Hello and welcome to the third session in Applied Maths. In the last one we actually were talking about projectiles. Now these projectiles were in a particular case. They were where they were fired and the ground was horizontal. Now some of those problems you could find that you're on top of a cliff and that there's, let's say, 100 meters of a drop down, but again it's going to be horizontal ground down there. The thing we have to deal with now is where the ground is actually sloped. In one of the two main textbooks on this, both of these two types of things are in one large chapter, but in the book that I normally use, the Conliffe book, it's in a different chapter. And I know why it's done that way, because there is a new concept brought in this inclined one. And the concept is changing your opinion from things that you've been used to for years, x, y, or even in vector sense, I, j. You're used to the idea of these things being horizontal and vertical. With this new type of problem in applied maths, the inclined ground conditions like that, if you fire something, what this chapter is going to do is it's going to tell you if we change our coordinate system, we can solve it. And what we're going to do is, instead of this ij system down here, or even thinking of xy like that at the moment, we're going to go and we're going to set up our coordinate system this way. J is going to go perpendicular to the surface of the ground, normal to it basically, and the I is going to run along the line of the ground. Now technically you can turn the page for yourself and you can be back in good old familiar territory where the I looks horizontal and the J looks vertical. But there's one catch, and that is when you do that you find that gravity doesn't pull down the way, it's pulling at an angle. And the whole issue here is we have to now solve a problem where gravity is going to affect both directions in the coordinate system. In the first set of problems, when the ground was horizontal, gravity only pulled on the vertical component, which was the j vector, and it didn't have any impact at all on the I vector, the horizontal one. Now it'll impact both. So what we have to do to begin with is, I'll just restart this line again. We have to look to see what happens if we fire something from here. There it is, it's doing what it normally does, and it would like to have continued. So it would have liked to have continued on there, but it doesn't get to. It crashes here on the incline. Just because the ground is inclined doesn't mean that our parabola is inclined. Our parabola is still balanced around a vertical line, okay, like that. The parabola doesn't rotate, it's just the ground is rotated. What that basically means is, if we look at the original ground conditions, which were horizontal, we knew that when this went flat, that we had reached the greatest height. It meant that there was no vertical component. The only thing that was keeping the projectile moving was the fact that there was a horizontal component working on it. At that top point here, if you remember, the effect of gravity was that it had neutralized the vertical component of velocity. It had no effect on the horizontal one. Now we need to set up a situation where we're going to look at ground which is sloped with an angle h, and now we'll say the start velocity, or sorry, angle here is p. and we have set up our little coordinate system over there. Now notice something. It's really important for you to draw your little coordinate system, because very often you will turn your attention to it. And what I want you to notice is, while this thing is moving up, pick any point, let's say along here, while it's moving up the way, we can split it. Oops, I just did that wrong. We can split it into a piece parallel to the plane and a piece perpendicular to the plane. Now you notice that because it's moving up the way, the perpendicular piece is facing up the way. So it's plus, it's a positive. It's positive because it's in the same direction as the unit vector. Over here, when it's falling, when it's going back down the way, if I break that into its components, we'll say a horizontal bit and a vertical bit. The vertical bit is now acting down the way. In other words, the projectile is being pulled down. Because it's acting down the way here, it's acting in the opposite direction to the unit vector j, and therefore it's going to be a minus. One of the things you always watch for in applied maths is to ensure that you get your signs right, and the signs have nothing to do with anything other than how is the thing moving relative to the unit vectors. It's pretty clear that as it's still rising, that the vertical part here is a plus because it's in the same direction as the j vector, and as it starts to fall way over on the right hand side, it's clear that because it's dropping, it's going against the direction of the j vector, so it'll be a negative. It's going to be a minus over there. What about gravity on this thing? If we look at gravity, see, it's happily going that way. What we have to do is to break it into two bits. We say a bit that is parallel to the slope of the land and a bit that's perpendicular to the slope of the land. Now what you will notice is that it's actually, because it's acting down the way, gravity pulls down the way, that this one is a negative because it's in the opposite direction to the j vector. Okay? What about the other one? Well, we know that if we travelled this course here and then off down here and finished up down at where I've drawn G, it would be the same as if we took the shortcut, which is the line that gravity acts on. Both of those are acting against, both of those short lines, that one and this one, are acting against the line of the two unit vectors, so I'd expect that to be negative 2. Okay, so we'll have two negatives. What's the angle that we're dealing with? It's this H angle. So when we're talking about the gravity here, we're going to break it into components, and you're going to get, in this direction down here, you have G sine H, and in this direction here you're going to have G cos H, all because our two vectors, our unit vectors, are related to the slope of the ground. So it's the H, and this is very important and I'm emphasizing it for good reason, it's the H angle that matters, because we're dealing with this angle here and because our two unit vectors are parallel and perpendicular to the ground. So that's for gravity. what about our velocity? Let's say our start velocity, whatever we want to call it. U is the one that's been used in the book here. Now that's interesting because U is running off up, but it's doing so with an angle P. So what we have to do is to break this thing into 2 bits. I'll just simplify the drawing a little bit now. We're going to break it into 2 bits, forming a right angle triangle. So instead of going up along the U line here, we could have run up along the plane, and we could run in vertically. So those two, that longer journey, can replace this journey. And the interesting thing is, the angle that we're now dealing with is this P angle. So when we break up our U vector, we will find that the angle we're going to be dealing with is the P angle, not the H angle. Okay? So running up along here, in line with the plane, you've U cos P, and going vertically, you've got the U sin P. So there, we now have broken down the components of the things that interfere with our little particle. One is the force that it was supplied to it to get it to move, and the other it's the force that is dragging on it, which basically is related to gravity. The equations we get, which are simply applying the 3 linear constant acceleration equations that we've been dealing with for the last 2 sessions, all we're going to get out of this, and we can, I'll write it over here, that at any point in time the velocity vector is going to be U cos P. It's going to be that in the I direction. That's the perpendicular to the plane. And it's going to be in the J direction. So how did we find that? Well, if we go back to the 2 triangles that we've drawn, the I direction is the one that's in line with the slope in ground. And we can see from the velocity one that this component here running up along the ground, which is the U cos P, it's in the I direction, so here it appears. If we go to the gravity one, we can see that in line with the ground it's this one, so it's the G sin H. That's why it appears here. And likewise for the other 2, U sin P and G cos H. And T is time. That's simply applying the V equals U plus Ft equation. The nice thing is we've got it in vectors. So all of that, we can say that V is equal to something multiplied by the I vector plus something multiplied by the J vector. We have converted a curvy line, velocity relationship for a curvy line, into 2 nice simple straight line ones. What else can we do? Exactly the same as in the previous chapter when we were looking at distances. What we can now say is x I'll do it over here. in the I direction. X is running up along the slope here. As we go up along the slope, we're saying X is increasing. What's Y? Y is now perpendicular to the slope. So if there's a slope like this, we're saying this is where Y is. It's going to be 90 degrees to it. We say, what's it going to be? Things are getting complicated. These are much longer and much hairier expressions than the ones that we had with the simple flat ground. Now, what you'll be glad to find out towards the end of this session is that you can actually solve all of these problems, these slope to line problems, by just using the previous ones. I'm going through these particular ones here because you need to be introduced to the concept of changing, of rotating, like up here, of rotating your unit vectors. This is extremely useful in other chapters. Basically, you got probably introduced to it at this one, and I'm just saying, grand, nice exercise, but by the end of this, I'm telling you that there is a different way, and we'll go and do it exactly as the same as the flat ground ones, so we'll find our answers much faster, and this should become an easier question for the Leaving Cert, and a one that can be done well inside the time limit. Okay, so let's have a look. Basically, the same type of set of equations are now going to get built, like got built for the flat line one. One of them is time. What is it? Now, I'll deliberately write it a little different to how it was presented in the book. That's time of flight. How long the thing was in the air from when it went bang to when it went bang. Okay? Now you just have to watch for one thing now, and again, you solve always by, redraw this. You always solve your problems by drawing drawings. That's the ground. This is the thing in air. It would have gone there. And we're saying, what's the time for maximum height? What's the maximum height we're talking about here? And this is important. These are our unit vectors. I vector and the j vector going in that direction. So that's the little I one. The I runs in line with the plane, and the j is going perpendicular to it. So the maximum we're now going to talk about will be when the slope of this curve becomes parallel, and you can see the slope of the line is varying, and we just want to find the location when it's parallel to the ground. That happens just about there, and we'll say here, right at that point, I've got the greatest height. Now that's the greatest height perpendicular to the ground. Okay, and under those conditions, the amount of time it takes, it's equal to half of time of flight. That's how much time it took the projectile to reach that location. It's important to recognize that that is, if the ground just disappeared away from there and we were left with flat ground, that the actual height we'd now be talking about would be way over here when the path of it is parallel to the flat ground. So the height, the maximum height that we're looking at here isn't the maximum height, we'll say, by way of off up into space, for example, it's the maximum height relative to the sloped ground. Okay, the actual greatest height it reached, if we picked as a datum, as a flat level, where it started from, the maximum height it reached was over here. Okay, what we're looking at is the maximum height above this sloped ground. It's a different thing. Okay, there's a curious point about this, because in the first chapter we found the amount of time it took from it starting to move to when it hit the flat ground. When we found out that time, we found it only took half the amount of time for it to get to its biggest point. So the same kind of relationship holds here. On the slopey ground, if you work out how much time it takes to hit the ground, half that amount of time will tell you the information you need to work out how high it got, the biggest height it got above the sloped ground. So there's a lot of parallels here. Now all we've got to do, obviously, in these, if I want to know, well, how high did it go? We had on the previous page an expression for y, the height at any given point in time. If I put in this time value into that y expression, we actually now find out just how high it got. The same way is if we put in the time of flight time, this one here, into the x expression, which x decides how far it's gone up in this direction. That'll tell me just how far it got to before it went bang. This is us looking at things being fired up a hill. Now, if we want to keep everything the same, what we always have to do now is we need to look at a situation where, what if we were up here and we went bang this time? So we're firing down a hill. Well, we should set up our coordinate system. This is still J, but the I one is going to be running down the hill. We're setting up the I to follow the line of the projectile will be going. So as the projectile is moving, the I values are getting bigger. So what we've done is alter these guys again. And once we do that, we can again go back to our equations for gravity. We can go back to our equation for the initial velocity, and we can develop the whole things up again. So then, can we simplify this? This projectile doesn't get to go this last piece down here because it'll hit the flat ground. If the ground wasn't there, it could go all the way over to there. So then, how can we work out when it's going to hit this and still use the original simple equations we had before? What we knew before was, okay, we only had one angle, an angle to the horizontal, okay, and I'll just call it theta to save confusion. And we knew that we could split this u vector into a vertical one and into a horizontal one. So if we want to convert the sloped ground problems, we need to be certain that we are using Q equal to H plus P. These problems will tell you what the slope of the ground is. They'll also tell you the slope that the projectile made with the ground when it started. And I'm just saying, add both of those angles together and we're back into our good old theta condition as before. Now then, that means that our little coordinate system is going to stay the same. I runs horizontal and J runs vertical. Why that's easier is now we know that gravity will only affect the J direction, it doesn't affect the I direction. So in the I direction, the velocity will always be equal to U cos theta. And we know that the value of x is always then going to be the horizontal velocity by time, which is U cos theta by t. At any point in time, I can very easily know how far over I am. Let's just pick, well, we'll go a little further. Let's just pick there. I know how far over I'll be. Once I know how much time it took to get there. What else can we know? There's only one more little thing we have to appeal to for us to solve these problems as simple as the first half problems. We need to find an expression for our sloped ground. And this is where very ordinary junior cert maths will help you. Geometry. When we write the equation of a straight line like this, we're saying the height y is equal to the slope, which is m, multiplied into the x, and there's a c added, and c is just how far we were above our origin to begin with. So this, where it hits the y-axis, is this point C. Now you'll notice up in our main drawing here that the line goes straight down and hits where the projectile is to begin with at the same ground level. So C is 0. So in this case here we can say this line there, the level, the height, we'll call it anything, I'll call it h, the height of this is going to be equal to mx. So at any given point in time here, if this is x, that's mx. And the good news is we know what x is. It's u cos theta by t. So this is m Now I know three things. I know how far we're going to be horizontally. I know how high up the projectile is going to be because I've got my y equation for the projectile. And I also know the height of the ground. And all we've got to do is to watch one little thing. There's a difference between these two. It was bigger over here, and it's getting smaller. When the height of the ground is equal to the height of the projectile they hit. Pretty obvious, I know, but it's important to recognize it because it solves your problems for you. We're saying it hits when y, that was your original y equation, okay, minus m we're saying when the difference between this y height, when that y height, and you take away the height of the ground from it at any point in time, and we're now looking at the difference between the two. So we have a nice little difference equation. When this difference gets smaller and smaller and eventually gets to 0, which is that, we found where it hits. Now, even though the type of questions you can be asked here have to do with what's the maximum the time of flight for the maximum height above the ground, we have learned something already from having gone through the previous questions, and that was when we know how long it took to hit the ground, half that amount of time tells us the maximum height that it reached above it. I work out that time, I half the time, and I put it into my equation for the projectile, and I'll find out how high it was. And we can still, same as before, find its maximum height above a datum of flat ground if you wanted to. The other type of questions that they have in these things here relate to, if the projectile meets the ground at a certain angle, and for example, the obvious one would be 90 degrees. I'll say this is the ground here. Here's the path of the projectile coming down here, and we're saying right when it hits the ground, it's 90 degrees. They're very easy to work out. For example, if we use the system that's in the book with the I and the j rotated, it means that if it's coming down vertically, that the I component, this guy here, that particular thing has gone to 0, because if it hadn't gone to 0, this would be still pulled across here, but it isn't. If it's coming down vertical, there's nothing pulling along the line of the plane. So your I component is 0. So when you solve for the velocity in the I direction equal to 0, you actually get this condition where it actually hits perpendicular. In the second method, the one where you still use the simpler equations from the flat ground situation, all you need to do, and we all know how to do it since second year in secondary school, and that is we just need to find out what this angle is relative to the ground, and it's easily worked out. We shove that in and we say, how do we work it out? Well, we're saying that the slope that it's going to hit at, I'll know the angle here, and the slope, when we know that angle, we just let the tan of the angle equal to that slope. And what's the tan? The tan is the j component divided by the I component, because tan is sine over cos, and tan is just another name for slope. We can solve them either way. Now, I don't mind which way you use. I just like to play around with both of them. One of the reasons I like to do it is because it shows you the amount of flexibility you have in applied maths. You can still continue with the old system, the horizontal I and the vertical j, and you bring in a new equation, which is this one over here, for the slope of the ground, and you come up with a difference equation, which is this thing here, and you can solve them, all of these type of problems. The other is you bring in the trick of rotating your unit vectors. You come up with different equations. They look a little bit more complicated, but you think your way through it, and you always draw drawings. There's one more little point that actually is made towards the end of this chapter. And I'm just mentioning it to you because whether it's on a flat thing or whether it's on a slopey ground, it doesn't make any difference. But if the projectile was elastic, and in other words, let's say like a sponge ball, that kind of thing, you know it's going to bounce. And you'd say, is there a relationship between these bounces? For the thing to bounce back, something's got to happen. It's going to compress, and that particular energy that's used in compressing it is going to give it the energy to reverse its direction and run off up the way. Now you think about this. Right here at this point, it's coming in here like that. We can break that into two components. this one and this one. So you can say, you can look at it like this, or you can look at it like that. What you need to understand is the component that goes in that direction doesn't hit the ground. It's only the component that goes in that direction that hits the ground. So when a ball or a projectile hits the ground, you will find, and especially an elastic one, you will find that it's only, and we'll just set up our terms of reference here. It's only the component in that direction that's actually going to have an energy loss. The other one, the one that's going along the line of the plane, doesn't have an energy loss. You're often given an energy loss which can be called E. So we might say if it was 10 to begin with, afterwards it'll be E by 10. And E, let's say, would be the efficiency of the amount of energy you've been left with now. And if E was equal to 0.9, you'd be saying, having started with 10, it'll go to 0.9 multiplied by 10, which is, it'll bounce back with an energy of 9. It only applies to the component that's perpendicular to the surface. Here's an odd thing about it. If we get that length and we also get that length, in other words, the length of two successive jumps, if we divide this smaller one by the longer one, the answer to that is E. It's the same E as this. It's the change in the energy component, okay? And you would find that all successive ones up along, as it continues to hop, will be dropping in size by the previous one multiplied by E. So let's say it was 0.9, as we were saying here. If the first one is 1, this is 0.9. The next one is 0.9 by 0.9, which is 0.81, and on and on. So you'll get a succession of jumps like this. Remember that this is still in a vacuum. We aren't taking in wind resistance or air resistance into account. So in a vacuum, and under these nice stylized conditions we have, you've got this lovely relationship between the length that it keeps jumping and the effectiveness, or the amount of energy that remains in the system when it moves from this first jump into the second one, and from the second into the third. After that, the other types of problems that they have in here is just you playing with a little bit of algebra or trigonometry. Remember, and it's so important to remember this, that you always confirm the direction that something is moving in when you're solving your problem. You confirm it relative to your coordinates, to your I and j. If it's going in the opposite direction, like remember j is going up the way, if the thing happens to be going that way, then we know the j component is negative. We know this component is positive, so the I is still positive. Okay? If it changes direction, you watch out for the need to put in a minus in whatever direction it's changed relative to these two little guys. There are a lot of very interesting questions in these books, and you could spend quite a length of time playing around with them. That's what I want you to do. If you have problems with these exercises, send us an email and we will deal with the problem. We'll give you an answer. Okay? Bye now.